Hello everyone, this is Samiti Mandal and today we are going to learn about how to design a suitable filter using pole zero placement method to remove the baseline wander from the given PPG data. So pole zero placement method, this method is used for designing narrowband filters like low pass, high pass, band pass, and there are other kind of filters which we can design using this method. Some of them are notch filter, comb filter, digital resonator and digital oscillator. We have to design the transfer function which is g into multiplication of all the z minus zk, all the zeros of the uh, in the z domain, and divided in the denominator it will be multiplication of all the z minus poles. So how to design some filter using pole zero placement method. The location of the poles and zeros affect the frequency response of the system. The zeros on the unit circle at specific frequency reduces the magnitude, whereas the poles at the specific frequency magnifies the magnitude response at that frequency. What are the constants? The constants are placing the pole in, we have to place the pole inside the unit circle, otherwise the stability will be reduced, like the outside the unit circle the system won't be stable, and zeros can be placed any location in the z plane. When using complex poles and zeros, we work with conjugate pairs because we have to get real coefficients in the difference equation. So let's look at the lab assignments. Remove the baseline wonder having the cutoff frequency fc equal to 0.4 Hz from the given unclean PPGC data of 10 seconds. Using a suitable design, you pole zero placement method. So as we have to remove only the baseline frequency of 0.4 Hz from the PPG frequency range 0.5 Hz to 5 Hz, we can use a high pass filter with cutoff frequency equals to 0.4 Hz. So we can design the using the same way we can design the transfer function, and for designing high pass filter we have to place the pole at some omega equal to pi, as because we want in the high pass filter we want like magnitude 1 at omega equals to pi, and at omega equals to 0 we should place a 0. So the 0 will be placed at the on the unit circle, and the pole will be placed at some distance inside the unit circle, and distance can be determined by the formula 1 minus fc by fs into pi. So basically, if we take the transfer function and get the differential equation from the transfer function, we will get something like y of n equal to r into y of n minus 1 plus g into x of n minus x of n minus 1. This is for the high pass filter transfer, like time domain differential equation. So in the code we will write this one only. So we have declared the input array and we have stored the PPG data given at like 80 Hertz sampling frequency. Then we declare the output array and some in size equal to 800, fc equal to 0.4 and fs equal to 80. Now in the void setup, serial dot begin equals to 9600. Then I am calculating the r, that is the distance of the pole from the origin. That is 1 minus fc by fs into pi. And depending on the r, we are calculating the gain g equal to 1 plus r by 2. So now I am using the differential equation to get the output array that will be giving the PPG signal without any baseline wander. So in the void loop, I am printing the output and input at the same time. So as you can see, the input is the blue one, input PPG with baseline wander, and I am extracting the PPG signal without any baseline wander, that is in the red color. So our second question was synthesize the baseline wander with frequency 0.1, 0.2 and 0.25 Hz and add it to the clean PPG signal. Now remove the added baseline component using the previously designed filter. Check its accuracy by estimating mean square error, root mean square error and SNR. Sorry, I did a mistake here. It should be 0.2. So let's get back. Now we know our error equal to input PPG minus filtered output. Now mean square error equal to error square divide. We have to sum up all the error squares and divided by n. Root mean square is the root of mean square error. SNR is 10 log input PPG square divided by output square, error square, sorry. So what we are doing, we have declared the input array, but this time we have taken a clean PPG signal, that is no baseline wander is there. We have taken declared the output array, and I have declared the three, like noise, for three noises I have declared three 800 arrays. Now I have declared another array L and F and error for E. Now I am declaring some variable mean square error, root mean square error, SNR, signal, and FC equal to 0.4, Fs equal to 80, and int equals to N800. Now in the void setup, serial.begin equal to 9600. Now I am generating the sine waves, that is the baseline wonders. I am not giving them all amplitudes, one different amplitude I have given 0.2, 0.3, 0.4. So I have summed up all the baseline wonders to L of I, and then f of I contains the input signal, that is the clean PPG, plus all the baseline wonders. So in the computation part, I have calculated the R and G again, and I have applied the filter designed through Pole-Zero method. So up to this part it is fine. Now I have to calculate mean square error, root mean square error, and SNR. So for calculating, we have first calculate the error E of I equal to Y of I minus X of I, and MSE will be MSE plus E of I into E of I, that is E of I whole square. So we got the mean square error. Now not we have to divide it by n. So MS equal to MSE divided by n. This is the mean square error. Root mean square error will be square root of mean square error. And for calculating the signal value, that is for int I equal to 0, I less than n, I plus plus signal equal to signal plus x of I whole square. Now I have to do SNR equal to 10 by 2.3 into log of signal by mean square error, that is the noise. So in serial.print mean square error is, and I am printing the mean square errors, and in the plotting part I am plotting the signal. So as you can see, the blue one is the PPG signal actual. The red one is the added baseline. You can see the baseline, it is coming down, and the green one again gives the PPG signal without any baseline wander. So I have got the mean square error around 0.07, the root mean square error is around 0.27, and the signal to noise ratio is 30.46 dB. Thank you.